by the mapper, oh hey, here are all the locations where you can find the stuff that you are supposed to have. Now how do we decide what goes to what reducer? Well, the MapReduce authors just say, we'll just use classic hashing. We say hash the data, mod R, where R is the number of reducers, and I've numbered them 1, 2. So what words does reducer 2 get? Reducer 2 gets the words that hash to 2 after you hash them and mod them with the number R. Right? So the master knows all this. The master can do these computations. The master says to this reducer 1, hey buddy, here's the file on mapper 1 where you can fetch the thus. Here's the file on mapper 2 where you can fetch the thus. Here's the file on mapper 3 where you can fetch the thus. And by expectation, that reducer is going to have to go ask all of the mappers. The mappers have tried to write enough files that it's relatively easy for these guys to do this without stepping on each other's feet. Because they would step on each other's feet if they were accessing the same file, because this guy is also going to ask for files from all of the mappers. Make sense? You look confused, why? So if I'm responsible for the word fox,
right,
in a limit where I have all the documents that have ever been written, fox occurs in a great many documents, and since the documents are more or less randomly scattered around the network, I expect fox to be on literally every computer. Now, because words are Zipfian, that's not going to be true for all words, but it's going to be true for a great many words. Yeah?
So reducers are responsible for the shuffling and the combining. So what you're doing right now is the shuffling part.
Sorry, so did you say, I just missed the first part when you said users being responsible.
Are reducers responsible for 2 and 3?
In some sense, yes, because the reducers are the actors that are pulling the data. So like, the mappers are doing the mapping. The reducers, based on the instructions of the master, are doing the shuffle and the combine.
And what you just did was the shuffle.
That's right.
Okay.
So like, this is the shuffle. You shouldn't be surprised to see it, because it's all the all communication. Who's doing it? The reducers. But they're sort of dumb. They're only doing what the master told them to do. Right? The master said, hey, reducer 1, there's a 1 file here, there's a 1 file here, there's a 1 file here, and they're doing RPCs to do this. Although you could imagine that these guys are running NFS or something like that too. Yeah?
Does the master also handle essentially sharding?
Well, I mean, this is, I'm not sure if I understand what you mean. I mean, this is sharding, right? So like, the master has decided, you know, so the user, what does the user supply? They've supplied the map function, the reduce function, and they've also supplied the values M and R, which is like, how many mappers would you like to run this on? And how many reducers would you like to run this on? So this user said, oh, I don't know, 4, 2. Okay, well, given that there's 4 mappers and there's 2 reducers, and all the data needs to go to both reducers, then obviously there needs to be a sharding. And that's exactly what's happening in the shuffle phase. Right? All the reducers are pulling data from all the mappers, but what data are they pulling? They're pulling their shard. Like, this guy's responsible for this guy's responsible for lazy, this guy's responsible for fox, this guy's responsible for brown, right? So that is sharding. Right? We partition the keys. Remember, here, the data was partitioned by document. Here, it's partitioned by word. Yeah?
Is there a reason that the reducers are on separate machines than the mappers? Or is that just
They're not necessarily on separate machines than the mappers. But there wouldn't be that much benefit to placing a reducer on a mapper. It would only save us one of those edges. And I've drawn it this way to just show the roles separately. Everybody, like in Paxos, the master is just one of these dudes too. So you could have the master, a mapper, and a reducer all on the same machine. You would just have diminishing returns co-locating reducers with mappers. Unless there was some weird thing where there was no shuffle. Like, you happen to know that the map phase and the reduce phase were partitioned on the same key. Maybe there's some kind of pipelining optimization that you could do, right? Okay, where are we? So the reducers have pulled all the data. Oh, and then they execute the reduce function. They tell the mapper when they're done, and then control returns to the client. And that's it, right? It's too easy. So we supplied these things, and this thing just knew what to do. It scheduled the computation, it made sure that only 1 copy of every compute job ran, it tried to make it fast by placing it close and spreading it around a lot. It took care of like automatically knowing that phase 1 was partitioned on this key and phase 2 was partitioned in this key, so there needs to be all communication between these things, sharding on this key for things to go to the right place. If you didn't do that, you wouldn't get all the buzz in the same place and you wouldn't compute those right counts. Right? So it just took care of everything else too good. Any questions before I get into the fussy details? Questions? Would you like to use a framework like this?
definitely.
Yeah, sure. I mean, it's not that. I mean, it's, no, but the thing is like, how would you do you consider this to be an expressive programming model? Could you write a web server in MapReduce? Could you write MapReduce in MapReduce? I don't think so. In fact, yeah, the paper that I was telling you about, where we're advocating for this like logic programming stuff. Where we're like, distributed programming is really hard. It's really hard. You know what's easy? This certain class of distributed programming, data parallel programming with restricted programming models. That's like really easy. Wouldn't it be cool if you could take all the really hard problems and make them really easy by kind of recasting distributed programming as like data parallel programming? Yeah. MapReduce is a step in the right direction. But MapReduce isn't expressive enough because you can't like implement MapReduce in MapReduce. So let's come up with something that looks like MapReduce queries and use it to implement MapReduce, and then we'll show you that it's expressive enough to do full. So that's kind of the whole setup of the paper. All right, let's talk about fault tolerance. What could go wrong?
Computer crashes?
Well, obviously the master could crash, and then it turns out you're ass out if that happens. So let's talk about the other things that could go wrong and how it's okay. So what else could go wrong?
Some stragglers?
Well, we'll get there. But,
Some other computer crashes.
yeah, so like who? Okay, so
One of the mappers.
yeah, thank you. Okay, so what could go wrong? Mapper crashes. Yeah? So what do you think we should do? What do you think MapReduce does in the event that, like this computer is just gone. And it's in the middle of the computation. Like we started doing some tasks, we're doing some tasks, we're doing some tasks. This guy died. In fact, let's just be really precise. Let's imagine that the map phase was complete and reducers were already starting to do work. Right? Because if the map phase had just began, maybe just start again. Right? Who cares? But if you can get almost all the way to the end of the job and you have to start again, you might never finish. Right? So let's imagine that we're doing the reduce phase, but before the reducers have read all their stuff off mapper 1, he's just gone. He's never come back. What do you think?
Start mapper 1 on the other computer, on the replica.
So start all the tasks that ran on mapper 1, because there could be a great many of them, on, I don't know, mapper 3.
Yeah.
Okay.
What if that crashes?
So why is that okay though? Like remember, like in this class we learned that, you know, it would be great to make multiple copies of data in computation, because then you can survive failure. However, if you don't do so in a very careful way, you end up with inconsistencies, because there's all this uncertainty about the order in which things happen. So why aren't we worried about that?
If the mapper told the master that it's finished, then in that case you might be worried if the reducer has already started reading off of it. But if that happens, then you could perhaps invalidate that data. But if that hasn't happened yet, then you're at a rollback stage where you can just redo that computation, right?
Yeah, I mean, I think in general, the thing that I forgot to mention was at the very end of the reduce phase, we're going to write the result to that global file system where the input data was so that it can tolerate a failure. And that means that like the reducer writes the result not just to their local disk, but to like the globally distributed file system so that thing's replicated to a bunch of places. So after the reducer completes, the failure of the reducer is no big deal. Like there's no local data on the reducer. So to your point, if a mapper fails, we can reschedule the map tasks and then inform the reducers about the new location of the map tasks. Okay? And I'll also point out that although we haven't constrained the programmer, at least in principle, the map function should be a pure deterministic function. That is to say, its output is determined by its input. Now you can write whatever you want, this is Java, but the expectation is that these are pure functions, which means that even if I did read some of the data from over here on one of the runs, I'm going to read the same data in the duplicated text. That also means that if I had to reschedule, let's say a reducer started reading some files, and then the mapper crashed, and then that reducer had to be rescheduled on some other reducer. Even if this guy had written his stuff to the file system, the next guy will rename that file and replace it with something good, right? So it's always idempotent to redo the work. That is to say, if a reducer finishes and another reducer raced with it and finished first, who gives a shit? It's fine, right? Okay, so mapper crashes, run could be on all of them. In fact, that would be smarter, right? There's 100 map tasks that were lost on this. Instead of putting them all on one other computer, I should spread them out across all the remaining computers, right? Get better utilization on other machines. And you inform the reducers, right? You have to. The master has to inform the reducers because the reducers have to know which mappers to go get the data that was lost, right? Yeah.
What if there were documents on the mapper that crashed that we need?
But that's okay because we assumed from the beginning that every document is replicated k times. So there's other machines that those map tasks could run on. Or if there aren't, it's the file system guy's problem, not the map reduce guy's problem. The durability problem, outside my pay grade. Okay, good. What else could go wrong?
Reducer crashes.
A reducer could crash.
And we just do the same thing.
So as I just sort of argued, we could always schedule the reducer process in another place. But do we need to rerun the maps? No, we can just fetch the data that's there on the local disk. So in some sense, there's a big checkpoint between the map and the reduce spaces. If you can get to the end of the map, you're never going to have to go back beyond it again. And if you can get to this side of the barrier, you can, and routes are flapping and tornadoes are going through data centers, you can keep retrying from here so you have a better chance of finishing. You never have to go back to the beginning. Make sense? Reducer crashes. Restart. Atomic rename deals with the fact that we might have multiple reducers racing the right result. It doesn't matter. Whoever gets there last wins. And guess what? They both wrote the same thing anyway. So who cares? Okay. What else could go wrong?
Master crashes.
Yeah, we'll put your ass out if that happens. Like I said. I can think of one really good one that's in the paper.
Yes.
Really? Interesting.
What if we expect these to be documents, right, with ASCII in them, but there's some crazy binary in there, there's some crazy UTF-8 character that causes our mapper to segfault. Are we fine?
You're never going to get past the map.
No, we're not fine, right? The task will never finish because the map test fails, and it gets rescheduled, maybe in the same place, maybe in another place, and it fails, and it gets rescheduled, and it fails, and it fails, and it fails, and it fails. Yeah?
So the master would then have to have some way of detecting if some task that it schedules is crashing multiple mappers and refuse to run that task.
Refuse to run the task. You mean like refuse to run on that particular document that it thinks is responsible for the bad thing? Yeah, that'd work. Yeah.
Does the master know the difference between a segfault inside the task and then just the whole mapper crashing?
It doesn't. So that's the problem.
Yeah.
That's the problem, right? It's like, from the perspective of the mapper, it's like, oh, I didn't hear back from that task, its heartbeat, and that looks the same. And so the mapper wouldn't, in a good way, be able to distinguish the difference between a poison input and something just going wrong. But your point though is that, let's say 100 times in a row, I tried to open the same file and it failed. It might be reasonable to say, there's something wrong with this file. So it's really actually kind of a cute trick what they do. So they have mappers multicast.
Still full though.
They have mappers multicast what they call a last gasp packet before processing every record.
Oh.
That has the contents of the record. And mostly they ignore the multicasting problem as well. Or they have a really short retention policy. But in that way, you know what was the last record that every map task tried to process. Right? And so if you're able to see, like, this is the bad record, then the mapper, next time it schedules the task, can say something along the lines of, process this whole file except for line 340, because I don't know what the fuck is going on with line 340. So isn't that cool? That's like just some real, something that is nice about Google papers is that, like, they actually built this thing, unlike most grad students. And so like they had to deal with like real world stuff and they had to work around it, you know. And so engineers love reading these papers because if you work on real stuff, you've always seen stuff like this. Like it just keeps crashing over and over and over again.
So there's some threshold for if it crashes like 1,000 times, then it's
Something like that.
allowed.
Yes, they start doing the last gasp and then very quickly sort it out. Okay, so program communication. Oh good. Scheduling, fault tolerance, locality. I even did. I'm not using the board anymore. Okay, so which brings us to stragglers, right? So let's imagine that this guy is slower. He's an order of magnitude slower than everybody else. What do you think we could do?
If we could take one of its tasks, tell it to stop it, and give it to somebody else.
Tell
Or
it
if
to
it hasn't
stop it.
started one of them yet, or...
Why would we tell it to stop it? Because let's imagine that this is how long it's going to take this straggler guy to do it.
Right.
And he's here. Right? This is how long it's going to take some fast guy to do it. We would wish we hadn't told this guy to stop.
Right.
Yeah.
Just start his task on some other machine, and maybe it'll finish first, and maybe it won't.
And
Like, just make
why don't I
race.
care about the fact that the things are racing?
Because who gives a shit? They're writing the same data.
They're writing the same data, and whoever gets there first, doesn't matter who they talk to. In fact, even if they both finish and the reducer talks to both of them, it's fine. This is called speculation or speculative execution. And the way that this is going to work is, the mapper is going to have a sense, I'm the mapper. I'm remembering all the tasks, T1 and who's doing it, T2, who's doing it, T3, who's doing it, T4, who's doing it. I'm remembering them all because I need to know when they're all done. Because then, and only then, do I switch to the reduce things, right? And so I'm like, okay, cool, this guy's finished, and this guy finished, and this guy finished, and at some point, I'm going to be like, I don't know exactly how they do it, right? But at some point I'm going to be like, this guy has gone for long enough that it probably makes sense to just, I think odds are good that it's going to take about that long, right, to finish this task if I schedule it on some T5, right? So once I detect that a task is nearing completion, but there's some node or nodes that are slow, I'm going to take the tasks that are running on those slow nodes, and I'm going to make a second copy of that task and run it on another one and let them race. You know, it's like, this is an advisor strategy for grad students sometimes. You give the same task, you give a task to a grad student and they're going too slow. And then after a while you give the task to another grad student because you don't care who finishes it. You just need it to get done, right? And then sometimes having given the task to two grad students, they both go fast, right?
The best in the room, right?
What? It works great. So that's okay. So here's a question. Why didn't I just make that speculative copy of task T1 at the beginning? Or in the limit, why don't I just make speculative copies of all of my tasks? Because if I had started at the beginning, I would have gotten finished a lot quicker. Right? If I wait until I know there's a straggler, I know that I'm not going to finish in a timely way already. I'm just trying to mitigate how bad it could be. So why wouldn't I schedule these things more aggressively? And in the limit, schedule them right away. And in the limit, schedule them all.
Wasting work.
What?
Are you wasting work doing
You're
that?
wasting work, right? But I'm wasting work anytime I speculate. Right?
It seems like you would want to do that so that all of your computers are running at full capacity all the time.
Wait, so you're saying you would want to speculate everything
Why
because
wouldn't
you think that running at full capacity is a good in itself, even if you're not doing good work?
Like if stragglers are a constant that you're gonna have in every task, right? Then wouldn't it make sense to?
Well, there are going to be stragglers, right? But if I speculate every task, I'm only going to be able to do half as much throughput, right? Because if I do 2 times as much work for the same reward, I have half the throughput on that reward. So it is, the thing that we like to talk about in systems. It's a huge trade-off. right? Because there's these two things that you want, and they're at odds with each other. What are the two things? Like, what are we trading for what?
Latency for throughput.
We're trading throughput that maybe we have a little bit of an abundance of because we've over-partitioned a little maybe to lower our latency. We want the jobs to take less time, and in order to make the jobs to take less time, we're willing to do some work 2 times. And it's all about smart scheduling, how you navigate this trade-off. Yeah?
How did the master know that T4 was getting slow and that it wasn't poison input?
Oh, because every mapper and reducer that has been contacted to do a task is going to periodically check in. Now, obviously you need to check in at the end and say you're done. But to make the job of the master easier, you periodically check in so that you know like your progress. So you imagine the master's like literally watching progress bars of all these things. And they start to get a sense when a bunch of things start to finish right around the same time, they're starting to say, everybody should be finishing around this time. And if somebody's taking a little bit more time than that, we're gonna like take a chance and schedule the computation again. And whoever finishes first, yeah.
Was there ever a chance that the function could accidentally be written so that it goes infinitely and thinks that it's progressing, but it's not?
The typical structure of the map functions is to emit things based on their input, so it's almost always going to be the case that they fall off. But nobody's chaining anybody's hand, so you could just write a divergent program, but then, well, then the computer would do what it was supposed to do, it just runs a bunch of map tasks that never finish. And, that would be really interesting, actually, to do, because then they wouldn't finish and they get speculatively executed, and I wonder how quick it would take for that to blow up, and then the speculative task gets speculated on. That might be a fun thing to do with the view. Just put a divergent program in and see what the hell happens. Oh no, we still have 3 minutes. Questions? Sorry. Yeah.
How do you ensure that map tasks idempotent?
Well, in some sense, like the assumption, which could be violated, is that they're pure functional. So in some sense, they're idempotent by definition because they don't have any effects, right? All they do is given an input, produce an output, and it's always the same output given the same input. So obviously, running multiple times doesn't have any effects other than running it one time. The thing that we're concerned about is the idempotence of sort of the effects of this computation, which is some new files being written into the file system that are the output of the reduce. And in this case, we get idempotence as a consequence of the idempotence of the rename operation. Right? If I have a bunch of files, wait, is that true? Is rename idempotent? No, of course not, because when you rename something, the original name isn't there anymore. So why is rename okay? Well, because rename is atomic. Right? Because I might have 27 reducers all trying to write the same file. And we expect, because these functions are deterministic, that they're all trying to write exactly the same file, so it almost doesn't matter what order they happen in. But let's just imagine that they're not. At the end of the day, we need there to be like one answer, right? And so, it doesn't matter that they're concurrent reducers trying to write two file systems, because when they write things, they call it rename. And rename, no matter how many of them are running concurrently, there's only one like final rename, right? So we have one copy of the file. So it's about atomicity, not idempotency. Right? Rename isn't idempotent. If I rename food a bar, well, no, then the next time it gets there.
Yeah, like either you would get there or it would not.
Well, if it didn't matter, it would be. Alright, so everybody please try to be here on Monday for Pat's talk. And it would also be great if you could attend this other talk at 1 o'clock. Singularity.
So you don't have an office hours that day?
What's that?
So you don't have an office hours on Monday?